This video will be on Newton's second and third laws. It's a continuation of chapter 4 on forces, and we'll be looking at sample problem C. So you'll be doing practice problem C after finishing this video. So what this video, once again, is going to concentrate is first off on Newton's second law of motion. Some things that you need to know about this is that you're going to be talking about acceleration and mass and its relationship to force. So letter A here says the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the object's mass. So what I want you to break down here, like in that little space after the word mass, is what equation are they talking about here? Okay, so let's read this one more time. It says the acceleration of an object is directly proportional to net force acting on an object, and the acceleration of an object is inversely proportional to the object's mass. So real quickly, guys, jot down what you believe the equation would be from reading these words. Seriously, write it down. Okay, so the equation that you should have written down is F net equals ma net. Okay, that's the equation that'll denote Newton's second law. Also, you know how like in the first law it said law of inertia is another name for Newton's first law? F equals ma is another phrase slash name for Newton's second law of motion. So what we're looking at here is, if F net equals 0, that would mean that there's balanced forces working on the object. So in your mind, you're kind of thinking, okay, on the free body diagram, to get an F net in the x direction to be 0, my F applied needs to be equal and opposite to my F of k, or my Fs max, depending upon which way it's acting. In other words, is it at rest, Fs max, or is it in motion, F of k? Or F net in the y direction needs to be equal to 0, would mean that your F of n is equal and opposite to your F of g vector on your free body diagram. But what B is talking about here is unbalanced forces. So real quickly, what do you think an object's doing if there's unbalanced forces on it? Well, let me give you a little helpful hint here. If you can look at, in a second I'll tell you which one. If you can look at a variable and say, oh, it's not equal to 0, therefore there are unbalanced forces acting on this object. Therefore the object is, and that's ultimately what I want you to see out of this. Okay, so let's jump back. I just said, oh, that value is equal to 0. Well, if there's unbalanced forces, then your net force, your F net, is going to be equal to some non-zero digit. Makes sense? So you're going to have like 3 newtons or negative 3 newtons for your answer, not 0. Okay, if you have an unbalanced force, what would your vector lines, sorry, that came out wrong, what would your vector arrows, resultant lines, vector arrows, look like on your free body diagram? They would not be equal. They would still be opposite each other, but they would not be equal. One vector would be longer, i.e. shorter on the opposite side, than the other vector that you're assessing it against. So for instance, the object is accelerating towards the right, it's speeding up. Your force applied vector would be longer than your F of k vector in the x direction. You kind of seeing this in your head? Like, I purposely don't want to write this down because by now you should be pretty comfortable with the idea of free body diagrams after assessing your free body diagram worksheet. And then the back of that worksheet will also assess as well. Okay, so with that in mind, and I kind of sort of told you the answer to this already, if your F net is a non-zero value, what variable, either m or a net, what variable has to also not be equal to 0? Okay, well, you should be thinking, Miss Arter, it'd be a lot easier if you told us which one is held as a constant, right? Because there has to be at least one variable that's being held as a constant. Think about this, guys. Are you losing mass as you're walking down the hall? Is your car losing mass as it's traveling down the road? No, so it's going to be equal to your constant, m. It's going to be equal to your constant. So therefore, you are assessing the relationship of acceleration to F net. So if your acceleration is some non-zero value, i.e. speeding up or slowing down, then your F net is also going to be equal to some non-zero value. So the idea that you can quickly say just by reading a problem, oh, there's going to be unbalanced forces working on this problem, is because it says the object is accelerating, i.e. speeding up or slowing down. So it's all about acceleration. So once again, the really big thing that I want you to get from this slide right here is, if there are balanced forces, then that means that one of two scenarios is occurring. The object is at rest, or the object is moving, but it's moving at a constant velocity, right? Because if you're at rest, VI equals 0, therefore your acceleration is going to equal 0. And if you're moving at a constant velocity, your cruise control is set. With me? Okay, so if your cruise control is set, then that means that you're not touching the accelerator, nor are you touching the brake pedal. So you are literally not accelerating. Your acceleration value, 0. You're not doing it, right? So if you have no acceleration, then you have no net force because they are equal. Well, let me rephrase that. They are directly related to each other. All right, so if you have unbalanced forces, that means that you're either speeding up or slowing down. Therefore, your acceleration would be some value. Therefore, your F net would be some value. All right, moving right along, guys. So here, once again, is this flow chart. So based on what I just told you, you should be able to understand this. Forces are unbalanced. Well, if forces are unbalanced, then that means that there has to be an acceleration. Well, how do you know that there's an acceleration? It depends directly on the net force, and it depends inversely on the object's mass. So once again, this is just reiterating Newton's second law equation, F net equals ma net. I'd like to add a few more things to this, but I'm going to change colors since that stuff isn't red. The acceleration. There is an acceleration. So if there is an acceleration, then that means that the object is either speeding up or it is slowing down. So in other words, you have some non-zero velocity or no constant velocity. Doesn't that make sense? Okay? Because if you have a velocity of 0 meters per second, then you would have no acceleration. You with me? Okay, good, good. So then if you also are moving at a constant velocity, you're not speeding up nor are you slowing down because you're moving at a constant velocity. So both of those right there, the stuff that's in the parentheses, this right here, is going to give you an F net of 0 newtons because A net is going to equal 0 meters per second squared. Therefore, you have balanced forces. Okay, guys, moving right along. So once again, here's your equation. Obviously, it's important. It's the third slide in a row that you've seen it. And I want you to look at the relationship between the variables. So you're going to be nice and help out this driver that her car just stalled out and she needs to move it. Well, you can totally do this. Obviously, you first have to put the car in neutral. Okay, so the car is in neutral, and you're going to apply a force and apply a force and apply a force. So with this force, you're going to give it a small acceleration, right? Well, this small acceleration is because it's extremely massive. Well, what is going on here? The object is at rest, right? So what do objects tend to want to do? Oh yeah, tendency. Where have I seen that before? The definition of inertia, tendency to resist change. Okay, so it's resisting wanting to move. So it wants to stay what it's doing. Oh gosh, that sounds very familiar. Where have I seen that before? Objects trying to do what they're currently doing. They want to resist change. Law of inertia. Oh, Newton's first law of inertia. Object at rest wants to stay at rest. Object in motion wants to continue in motion unless acted upon by an outward force. You're applying a force. You're trying to move it. So although it's a small force, you're not going anywhere. So now you're going to apply a larger force, so you're going to see a larger acceleration. In other words, the car's going to move. All right, so that's really all that I want to show you here. Obviously, the common variable, the variable that's staying constant in both of these pictures, is the mass of the car. The mass of the car, technically plus driver, is not going to change at all. So let's look at this sample problem here. It says Roberto and Laura are studying across from each other at a wide table. Laura slides a 2.2 kilogram book towards Roberto. If the net force acting on the book is 1.6 newtons to the right, what is the book's acceleration? So going through this problem, you know that you have a mass of 2.2 kilograms, and you have a net force of 1.6 newtons to the right, so it's not to be a positive or a negative. Yeah, that should be a positive because it's going towards the right, and right is assessed as a positive quantity. So then you want to solve for the book's acceleration. So technically it's a net. that you want to solve for in meters per second squared. What's the original equation that you want to use, guys? The original equation should be F net equals M A net. We want to rearrange this so it says A net equals, therefore you want to divide by M on both sides to get A net all by itself. Units look great, so we don't need to convert anything. Get your calculators out, please. Grab your calculators. 1.6 divided by 2.2. Please put that in your calculator. 1.6 divided by 2.2. Let's jot down that calculated answer. You should see 0.7273. Look over here at your givens. How many sig figs for your givens, guys? Yeah, you should see 2 sig figs. What's the 7 do to the 2? It rounds it up. So your final answer should be 0.73 meters per second squared equals A net. Fantastic. Okay, so now you'll want to do the practice C problems from this. Please make sure that you do click on chapter 4 practice C problem answers so you know how many answers to expect when you do the practice C problems.